how many nodes you need to give, and so on. So this one you need to assess very carefully after you have understand the whole mechanism of the random forest algorithm. So after that you can just click apply, and then it's to go to the next one. And this one, after the model has been trained from the 70% of the data, and we can use random forest predictor. So yeah, and rename one of the predictions column name. I give this I rename as the predictions. So later on it will come out with another column with the predictions with the value of this concrete compressive strength. Just now we are giving the actual value, right? So after that, after the random forest algorithms has developed the by using the random forest algorithm to develop the model, so we will be having actual value that is we take there is the concrete compressive strength, there is the output variable that we measure from the laboratory, and another one is the predictions. So prediction value. So you can see from this prediction output here, you can see this actual value, this is the prediction value. By using the random forest algorithm, the model has been developed and then has giving out us the prediction value for this concrete compressive strength. And after that, by having this, we need to evaluate the performance of this random this model. Yeah, this model. So how to evaluate? Because the evaluation part is quite important, because as I mentioned just now, there are many machine learning algorithms or deep learning algorithm out there, and yeah, we of course when we want to develop using this algorithm, we want to have a best accuracy as possible, so that it is near and it can be actually predict nicely, especially when we are doing some of the construction work. So to predict accurate to get the accurate value is quite essential. And after that, we need to evaluate. So you can so this is the evaluations result. For example, R square is 0.894. This means the data has been fit successfully with the 89%. And the data has been fit successfully to the model with 89%. And the prediction error you can see is quite low. So yeah, we can see, right? So later on, in future, you can also use other algorithms and compare their performance, and you can pick the best one to do the next analysis. Yeah.
I think another thing, this accuracy was calculated based on the training and testing, right? You have used 80-20.
Yeah.
So once this model is good, then just to let the students know, this example is being used, okay, to develop a model, and this is only training. It's only training and testing, right?
Yeah, doctor.
Let's say, for example, you have one new data set coming. You have taken the measurement today with the set of parameters. You give it to the model, and the model is going to give it a prediction for you. Okay, that's the point. Yeah, because this data is being used to develop the model, and the model, you keep the model. Okay, and the point of having a model, a prediction model, is that so that in the future, if you have a measurements, you just fit the the new data into the model, and it will straight away give you the prediction.
Yeah, if we have the testing, another testing data, if we measure from the lab.
Yeah, it's
Okay,
not a
so
testing data. It's we call it just like new data or unknown. Yeah,
new data.
yeah, that
So
we
we
can.
can feed it to
Yeah,
the model.
yes, yep, and then it will tell you directly what you can do in this experiment as well. You might split the data into training, testing, and validation.
Yeah.
Yeah, just to what you call it, just to be really 100% sure. Yeah, but that's another issue lah. I think this one is that one is another issue. Okay, but just to get the student the understanding of why we do prediction in the first place. Okay, it's because we want to work with new data. In the future, you just feed the data into your model.
So the data can be can be the parameters, the input variables.
Yeah, of course, the data will have the same format. Okay, the same information about the parameters. The only the new data will not have the compressive strength information because it's unknown. It's a new data. Okay, the one that you are using now, the data got the compressive strength because we are using it in the development of the model.
Yeah. Basically, in the truly term is actually the training validation, and then the new data is the testing.
Yeah, you can
So
split that like that, or you can have totally new data. But the problem with totally new data is that you cannot check the performance. Yeah. Okay. But if you have a training, testing, and validation, you can know what is the accuracy of the validation because it is known, but you just want to test. Yeah. You got what I mean?
so you guys get it right.
Okay, anyway, maybe because they haven't done it by their own, they cannot see the issue yet. Okay, but it's okay. We just the point here is just to expose you of what predictive analytics is all about. Okay, you have proceed.
Okay. Okay. As okay, so I think without further ado, I will quickly discuss, means briefly explain the data visualizations and manipulation and aggregation. Later on, I will go to the part two. There's also the predictions. Use, but there is a classification form. Okay, so this is just to calculate the basic statistical informations, and then to visualize in the histogram, because we can see our data distributions from in the form of the histogram. So this is how the our data has been spread for the wavelength 450. So later on you can expose later, and then scatter plot also is quite it's quite general. Later on you can try it later. And for these aggregations, we have the three we aggregation. If we want to aggregate the our our feature in by giving some of the criteria. So group, we can give it like that. For example, if the uh, we want to categorize our wavelength and to in the form of, I mean, the group class. So we need to our target is the class. So later on, the wavelength will be aggregate based on this class. So for example, but this is not a good example because this is the wavelength. I think it's not. So for example, in this wavelength 450, we want to count how many of them. So you can see in the wavelength 450, there are 99, 100, 180, and 60, right? So it has been calculated based on the class as a group. And this is the mean of the wavelength. And yeah, this is the mean of the wavelength. You can do it like that. Yeah, you can do it if you want to calculate mean, maximum, and minimums. So you can just group means put it as a target. Target is a group, and then later on aggregate the informations with the with the selected column. And I think I go to the last one for this first part, the workflow, the conversion of the workflow to the meta node. Let me take copy and paste it somewhere. So, okay, so actually meta node is just if you want to, if we can group or we can merge partitions or group of our certain analysis stage that consists of the nodes in one in one component that's called meta node. So if we want to merge these two into one, you can just click create meta node, and then this is for example, this, if you are running machine learning analysis, you can just, and these two is the pre-processing for this whole workflow, so you can just combine them, and later on yeah, you can double click and see it inside. So I think without further ado, I go to the second part. Okay, I think for the second part, I will straight away go to explain the machine learning workflow on the classification of soybean disease. Okay, so I will use this as example. I will just jump to this part first. With this derivative analysis, later on you can try it on your own. later on. If got some times later, I can show it also. This derivative analysis is the pre-processing analysis for the 1D hyperspectral data. And okay, now I go to this main important part first. As I shown just now, is the we have seen how the machine learning, one of the general examples on the predictions of compressive strength using the ingredients or the constructions material, right? So that's the regressions in the form of regressions. That means we give the parameter in the numerical form. There's the quantitative form, and then we predict our output and our output variables will show in the numerical form or the quantitative form. So that's called so in this case, in that cases or previous case I showed just now, it is regarded as the regression analysis. But now we have class 0, class 1, class 2, class 3, class 4, right? So it is regarded as the classification. So we want to do the predictions on the classification of soybean leaf spot disease using machine learning algorithms. Okay, so this is the workflow. This is the simple or general machine learning workflow we should understand. So the first is to loading the data, assessing the data, and then to do some pre-processing. Before pre-processing, we need to assess our data whether it is normally distributed or not. That is regarded as the exploratory data analysis. After that, we need to decide which pre-processing technique we need to use. So this is the this the very pre-processing step before we feed our data into the model. So for example, in the case of the previous case on the predictions of the concrete strengths, I use normalizations and I use min-max method. So we need to decide and these decisions or the method that we decide in the pre-processing step is depend on our nature of the data. So after that, we need to feed our data into the model to build, to train, or to develop the machine learning algorithms. And after that, we evaluate the performance based on the developed model. So without further ado, okay, I also show to you guys just now the nature of, the data, the raw data for this soybean, right? So leaf disease. Before that, before I go into this, I would like to show to you. We can, for this, we need to always plot the spectral signature first. As I have shared to you, as I have shared to you, okay, so I, in the plot underscore spectral tree, so we need to plot, because as the hyperspectral data, we can plot the serotic gas in the form of the spectral signature. So we know Okay, so we know the spectral reflectance of each class versus wavelength. So you can see from here. Okay, from here you can see class 0 to class 4. So it has the subtle differences across the uh, wavelength in the spectral region from 450 nanometer until 1000 nanometer. So you can see, okay, so class 0 is the healthy one. So of course it will have the lower reflectance in the red region. Red region, if you still remember in the electromagnetic spectrum, it is from the 600 nanometer to 700 nanometer. There's the 0.6 micron to 0.7 micron, and then after 0.7 or 700 nanometer, it is the near infrared. So later on you can, yeah, you can plot. And now we go to the important one. Okay, so we will be using the two approach of the data splitting or data resampling, which is the training and testing split or cross validations. So I have also shown to you just now with the in the previous case prediction of concrete strength. I'm using training and testing split. So later on, I will also demonstrate using the cross validations. So, okay, so here basically we have basically the flow is general as I shown just now. The machine learning workflow, we need to always remember this: loading, accessing data, and pre-processing, develop the model using machine learning algorithms, and evaluate the machine the performance. So for this classification, we will be using support vector machine algorithms, logistic regression algorithms, and random forest algorithms to develop our model. And then later on, we will evaluate them and to see which one perform the best by giving the highest accuracy. So, so before we move to that stage, we need to load our data and then um, do some of the cleaning. But this is quite subjective. We need to know the nature of we need to know the nature of the data first, and then from the nature of the data, because as we in future we will dealing with a lot of data. Every data have different circumstances, difficulty, because of their noise, and the noise is quite very the I mean the noise it can have can be very differently. Okay, so in this case in this case in this case because perform doing the pre-processing by remove the noise and is quite important before we feed to the model, because later on the accuracy or the output that we get will be incorrect. It will be very unnaturally from the real scenario. So 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 before that, we need to inspect, or we need to learn the nature of the the data. So as we can see, we have wavelength. This is the mean spectral reflectance, and this is the class. The class represents 0 until to 0 to 4, right? But this is classification. This is not regression. So this is the class is the category. It is in the form of category like A, B, C, D. But now we are giving class 1, class 2, 0, 1, 2, 3, 4. So to represent, so that the later on the machine learning when it perform, it will be follow this means this kind of rule. Okay, so but now I we know that this class is the category form. It is not represent the numerical form. So it is like the ABCD. So we need to do some pre-processing in order to let the later part, in the later part, the algorithm will know this class is the category, it is not the numerical. So it will not include into some kind of the mechanism in throughout the processing. So we need to use number to string. So from this number to string, we need to set, that means we need to assign this kind of rule let to so to for the later machine learning to know that this class is a category. So number class 0, 1, 2, 3, 4 is a number, and then now we want to uh, we want to emi- emulate in the natural form into ABCD. So string is the ABCD, because string, if you learn the programming later, string is the ABCD, uh, like that. We want to naturally emulate it for the class as ABCD. That's the string. Uh, so in order not to confuse the machine later. So that's the quite that's the one we have encountered, right? So for this data. So later on in this is still pre-processing step. So the first one I have make it to from for the class category. So from the number to the string. Later on, we later on if in the later on in the future scenario, we will get the data. We will not get a complete data. For example, in 2000, if we have the data from year 2005 until year 2021, maybe year 2021 we didn't have most of the input variables. So by that, if we didn't do this pre-processing or didn't do something, or and let it blank in the when we feed our model into the machine will become failure. I mean, will have the error. So 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 now, so of course we need to do something, like we need to run the mixing value and then to put the numbers as the mean. So even though for the 2021, if we discover the missing value, okay, we can use this missing value and then assign it as the mean to take the nearest means from the and calculated the mean for the year 2021. So later on, all of the data, our data will be have, I mean, will have all the informations. So this is to set that any missing value we need to you need to calculate the mean, take the mean from the previous one, and then the most frequent value. So as we come to this stage, all our information has filled with the value, or all of our data have all the informations. So after that, we can go to splitting the data into the training and testing, 80% and 20%, and we can do some normalizations. And for this, apply is just a normal procedure. After we need to, after we put the normalize, we assign the normalizations not to the to the algorithms, we also need to link it at the predictor. So later on, predictor will know there's a normalizations to get it balanced. So okay, so this is the machine learning algorithm. So as I mentioned previously, every algorithms have their own mechanisms, and we need to read and before we do the selections. So support, what is the support? What is the mechanisms of the support vector machines? And yeah, it has the mechanism. Later on, you can read it after the class, and because you can see with the I'm using previously I'm using random forest. The parameter is the tree in the forest, but in the support vector machine it has another mechanism and also their own calculations. Okay, so like for example penalty, gamma, bias, power, and so on. So and also polynomial, the highest order of the or the higher of the highest the order arrangements, radio basis, and so on. This all is included in the support vector machine mechanism. Okay, so you can find online how they work. And now at this one we can do the predictions. Okay, so uh, in this predictor is rename to rename and set another new column as a prediction class and probability value. This information we will be using on the evaluations, particularly on the ROC. So after that we click apply. Okay, so after the executions, you can see these the predictions 0. So you can see, yeah, I think the first one is the class. This is the actual output variables, and this is the predictions based on the model we have developed. 3 to 4. So it has some. The machine predict wrongly and so on. So later on, we need to compare our actual and the predicted one. And yeah, with the score. So we need to put first column is the class, our reference or actual, and then the second one is the prediction class. So we need to, when we are doing the evaluation, we need to put these two information, reference or actual value, and the second column is the prediction value or prediction classes. After that, we click execute, and then after that we need to we need to see the accuracy. So you can see the accuracy for this support vector machine is the 63% with the coherent kappa 0.539. Actually, this is not so good. So that's why we can adjust or we can tune the parameters from this. Based on this algorithm. So we need to know. We need to know first. The workflow or the mechanisms on the SVM. So after that, we can tune accordingly to increase the accuracy. Okay, so I think we still have 10 minutes. So for this logistic regressions and random forest, later on you can try on your own. I have provided here in soybean disease. You can just import this import 9 workflow, import the import this workflow by selecting import name workflow. So you can get that. And now I go to another approach of the data resampling. So we are using training and testing splitting, right? Now we are using cross validations. Cross validations. Okay. Initially, you can just Google and okay. Okay, cross validations. It has breaking down into it has assigned as a sorrowful. Sorrowful, that means the data will be assigned into the sorrowful, and then this full will be partitioned into the equally training and testing, and in each iterations the portion of the training and also the testing set will have the equal chance for uh, for training, used as a training the model, and also used as the testing the model. So as you can see, each of the portion for each, when it goes to the iterations, each of the iterations, each of the full have equal chance to be a training set, to be a training, and also have the equal chance to be the testing. So as you can imagine, to the previous one, we have seen training testing approach, right? We just blindly or randomly uh, break or split into the 80% to 20%, but we didn't but you can imagine by using this approach we can see it is less biased. I mean, we know at least they have the portion of the data has been can be equally divided, and to provide for the training and also the testing, so that the bias will be reduced as compared to the previous approach, training testing approach. Okay, so actually it's still the same. So but for the cross validations we need to use X practitioner. And how many validations, how many full, okay, validations here is the 5 or 10. So at here I assign 10, and then class column is class, and I put stratify sampling. You can study more with the difference between the stratify and random sampling. And random seed is the stability, to when assigning the the portions as the training and also the testing set. Okay, so so the differences for the node is the X practitioner and also X aggregator. We need to use X practitioner in before we fit to the model, and then after that we need to use X aggregator, because as we know, we have, I mean, cross validations has assigned into the full. So after that it need to get the, I mean, by that it need to get the average accuracy, not the best accuracy. We can say the average accuracy. I mean, for example, full one will give, for example, 80%, and then full two will give the 20%. I mean, I'm sorry, 82, and then full three will be 89. Full four is 90. So later on, this across as going on the iterations, so the result will be average, and then to give the I mean the good accuracy, so it is less biased. So this is so it's still the same, the concept. So we need to average out and then to get only one score or one accuracy. and uh, later on we just see the result. Although the result is lower, but it's less biased. But I mean the logistic regression is poor for the more class. I mean this okay. So we can, unless we use this random forest 88%.
Okay, how can you click on the X aggregator? What is inside it?
The prediction table and also the error rate.
Okay. Can you click on the X, another X partitioner?
Okay. This is yeah. This the yeah,
Okay.
doctor. So you can see, as I mentioned, the full will be averaged out with the error penalty, I think.
Okay.
So this one, right? Yeah, this the configurations, doctor.
Okay. Right.
And
Yeah, you have come to the final model, which is the random forest. I think for the students, probably I don't think they can really understand. What do you think at the moment? This is just an exposure for you. Do you understand uh, at least you know the concept, you know the overview of the flow. If you really want to understand what is happening step by step, I think we have to explain in a much more detailed way, you how, right? Because this concept is not easy to digest for the first timers. Yeah. Yeah, but it's okay for today. You are done, right? You how?
yeah, doctor, I'm done.
Yeah, you
Okay.
are done. Okay. So what you how has presented to you, I know it's a bit complex. Okay, but at least it will give you a general overview of what you can do with field spectroscopic data. Okay. Before this, it is very difficult to analyze field spectroscopic data because you have to use Python, for example, to do programming. Okay, which is quite difficult, especially for those with. I mean, it's not easy to do the program. Okay, even though you might be proficient, but there are a lot of things that you need to tweak and tune. Okay, but with the use of KNIME, all this programming, the requirement for programming is minimized. Okay, or we can say it's a low code or zero code data analytics platform. Okay, there's no need for you to use Python in this case here. Even though for more proficient scientists, they will still prefer to use Python because they can control many other things. But for most of for us engineers and scientists that don't have the level of proficiency in programming, KNIME is very helpful. Okay, for us to perform quick investigation and visualization and machine learning modeling. Okay, for our data. Okay, so what Yuhao has done here is basically he has presented you with a tool called KNIME. Okay, another tool that is quite popular is Orange, but yeah, I mean I'm using KNIME. Previously I used Orange, but KNIME is more. It's more, we call it, they got more, you got more community using KNIME out there, right? So KNIME is more fully, is better supported. And KNIME also give you the opportunity to, to do a proficiency test. Okay, you can take level 1, level 2, up to level 3 or 4, if I'm not mistaken, using KNIME, and you can get a certification. Okay, if you go to the KNIME website, they provide free level 1 certification nowadays. Last time it is quite expensive, but now they provide level 1 is free. Okay, so if you are interested, you can go to get your proficiency, which is free. Okay, you can use it for any sort of data. We have shown you using field spectroscopic data for plant, okay, for vegetation. You can see that it also can be used for civil engineering data as well. Okay, so it is relevant to anyone, okay, basically. Okay, so okay, this is the first part. Today, as a conclusion, we have demonstrated to you how we analyze field spectroscopic or lab spectroscopic data, which is the first level of data in hyperspectral as well as in basically in remote sensing in general, the first level kind of data. Okay, so next week, hopefully we can do some analysis using hyperspectral imagery, okay, either airborne or spaceborne. Okay, we're going to use the QGIS. Okay, but I think what I plan with you, how I think we can plan to have like a more comprehensive workshop on how to use NIME, okay, for analysis, because it is not, it is quite complicated to understand if you are the first timer, okay. So it's better to have a proper workshop, okay, to really understand how it works and how you can use it proficiently, okay, by using hands-on and so on. Am I right? How maybe this can be expanded, you know, this basically your explanation on the use of NIME can be expanded, okay?
Yes, doctor. Okay.
Yeah, there's a lot of potential to be expanded. Okay, so any questions from the student? Anything? Students has been very quiet. I'm not sure whether they are still around. You still have classes this afternoon? You got classes this afternoon or not?
No, doctor.
Okay, so very good. You can have a rest before the iftar time, right?
Yes, doctor.
Okay, so if you don't have any further questions, we can stop now for today. Don't forget to sign your attendance. Okay, so that's all today. Thank you very much, Yuhao, for the demo, okay, and the practical session.
Welcome, doctor.
And also, thank you very much, everyone, for coming today. And I'll see you next week. Okay, thank you very much.
Thank you, doctor.
Okay,
Thank you, doctor.
have a good weekend.
Thank you, doctor.
Okay,
Thank you,
all
sir.
right, thank you.
Thank you,
Selamat
doctor.